Polar coordinates. Let's see if we can clear some of this stuff up. Anytime you have a polar coordinate, they're pretty easy to recognize because this is an angle. Okay. So it wouldn't matter if it was in degrees or radians. It wouldn't change anything. You can tell it's an angle. So if I saw something like this, yeah, that's polar. I can see an angle sitting here. If I saw something like this, I see an angle sitting there. I know that's polar. Okay. If I see something like this, I'm expecting that to be rectangular, yet maybe polar if that was in radians, but you would have to be told that's polar. Because then you would have some decimal radians there, something like that. But otherwise, you would expect rectangular unless you're told otherwise. So this is your clue. All right. If I gave you something like this, I would say the polar point, then you know that's in polar. Okay. Otherwise, it looks rectangular, you would be expecting rectangular. Everybody okay with that? All right. Directed distance. This is a lot easier than it sounds. If you picture, we'll just do like that right there. All right. So this is what you did in basic trig. Okay. You said, well, all right. Here's X. Here's Y. So that was the point XY. Look familiar? Mm-hmm. R. It was really the hypotenuse, right? Do you remember why we called it R?
It's the radius of the circle.
R for radius of the circle. We have a circle coming around here. It referred to the radius of the circle. Yes, it was still the hypotenuse, okay? But it's just R. Rectangular, polar. X squared plus Y squared is R squared. Pythagorean theorem. First started out as A squared plus B squared is C squared. If you just had some generic triangle out there in space. Then it changed to H for hypotenuse. Then when we started working, or when you started working in circles and trig, it went to R for radius. But it's all still the same Pythagorean theorem. Everybody okay there? Mm-hmm. This was your angle. So this would be the rectangular point XY, or the polar point R theta. Using the distance, which is the hypotenuse, and then whatever angle you're at. Everybody okay there? All right, we'll come back to this directed idea in a second. These guys, these conversions. Well, that one should look pretty basic. Tangents, opposite over adjacent, or if you're working inside something like that, figure y over x would be opposite over adjacent. Everybody agree with that? These two. They look different, but it's what you've done before. Let's look at cosine, for example. Cosine. You originally thought of as adjacent over hypotenuse. Everybody agree with that? Okay, so then if you look at this triangle, cosine would be x over r. Adjacent, hypotenuse. So x would be r cosine theta if I multiply both sides by r. That's where that came from. It's really the same thing that you're used to working with before. You just usually saw the r over here and an x over r. Everyone okay with that? Not here. And the same idea with sine. For you, sine was opposite over hypotenuse, which would be y over r. R going to both sides. It's going to get you back to this. So when you reach the polar or started working with polar, you start thinking that you've got a whole new set of equations. You really don't. You have the same ones you've been dealing with all along. These two are written in a little bit different form. Okay. This looks strange with the word directed. The directed just means you could have negatives in there. So for example, if I had, say, the angle pi thirds would be about right there. I'll make something up there. if I had negative 2 pi thirds, down the bottom, just meant we were going backwards around. Does that look familiar? All right, so a positive angle meant you were going counterclockwise, and then a negative angle, you were moving clockwise around. Everyone okay with that? That was the idea of directed. You could have a positive or a negative. Directed R value. R refers to a distance. It's the distance from the origin to whatever the point is on the circle. It's referring to a distance. Distance is positive. Okay. If R is negative, it just means it's going the opposite way. The reason distance is positive is because distance is referring to the absolute value. If we talked about how far negative 5 was from 0 on the number line, it's 5 units. I know you're at negative 5, but it's still only 5 units away. That's why the absolute value of negative 5 was 5. It's referring to how far you are away from something. Okay? So, if I see a negative R, that just means I'm going to go in the opposite direction. Think another way to think of it that we've seen before in here, velocity versus speed. Speed's positive. It's the absolute value of velocity. Velocity includes direction. So a velocity of 10 miles per hour versus a velocity of negative 10 miles per hour, they both have the same speed, 10. One's just going forward, one's going backwards. Does that make sense? So that negative R means I'm just going the opposite way. I'm going backwards. And we'll look at some different graphs.
So would negative 590 be exactly the same as 270?
Yes,
Okay.
would be. So let's think about where these guys are. I'm going to give you, so work with this directed idea. So if we're just going to think about a quadrant. So I gave you the point 3, and I'll mix in some degrees and radians, because a lot of times degrees can be a little bit more visual for us. 3, 120 degrees. Always look at the angle first. 120 is in quadrant 2. And I'm going to go out 3 units in quadrant 2. The angle first clues you into the quadrant. So 120 degrees. Get a quick little picture here. Here's 120. I'm saying that's 120. And then I'm saying that's about 3 units. I mean, it's just an estimation. Going 3 units out. Everyone okay there? Let's go to negative 20 degrees. So think of the angle first. Negative 20 degrees. So I'm going down 20 degrees. So that'd be in quadrant 4. And then I'm going out 2 units. So something like this. There's 2. There's negative 20. And again, for polar, we're just estimating when we're sketching them out. We're not going to be using rulers and protractors and stuff. We can guesstimate roughly where it is. So I'm just saying, hey, this is 2 units long. There's 3. I'm just marking them. Let's go to negative 4 pi thirds. So bring in these negatives. First, think about the angle. What quadrant's pi thirds in? First, it's in 1. Okay. Now there's a negative R value. So I'm supposed to be in 1 up here. The negative R value tells me go backwards. So now I'm here. I am in quadrant 3. So the negative R value kicked me going backwards. Right. Now this is that idea of reference angles. You said it was in the first because there's a pi thirds reference. But when I go backwards for this negative 4, there's still a pi thirds reference right there. Through there. So the directed distance just means I'm either going for the angle, clockwise, counterclockwise. That's usually pretty familiar to us, positive versus a negative angle. The new piece is going to be this R value. So if it's positive, I'm staying in that direction. If it's negative, I'm flipping to the other direction. Is everybody okay with that? What this allows us to do, polar gives us multiple representations. And sometimes that makes it a little tough for us in math, because usually in math we like it when there's one answer, not infinite answers. We can do multiple representations. It means I can take that coordinate and represent it an infinite number of ways. So let's take something like this. Let's go 2 pi 6. So we'll look at some of the multiple representations. Best thing to do would be visualize where that's at. So this would be in the first quadrant, out 2 units. Does everybody agree with that? First quadrant, out 2 units, so I don't know, something like that. Multiple representations come in because I just want to end up back in that same point. So I could do 2 13 pi over 6. So I went all the way around. So I've got pi 6, and all the way around is another 12. There's 13. I'm in the same spot, out 2 units. Same location. Everybody okay with that? I could do 2 25 pi over 6. That just means I went around twice. How many times can you go around? As many as you want. So there's where you're getting those infinite amounts that way, right? This could keep going. Let's go the other way. 2 negative 11 pi 6. So negative 11, take me all the way back around, right here, out 2 units. Negative 11 pi 6 is in the same spot as pi 6. And then I can continue to keep going backwards. That'd be negative 23 pi 6. So on and so forth. I can go backwards around the circle as many times as I want. Another infinite set. I could also do negative 2 7 pi 6. So visualize where 7 pi 6 is. That's the third quadrant over here. And negative 2's kicking me back the other way. So I am in that same spot. So the negative R values give me 2 more infinite sets. Going positively around the circle or negatively around. So this one would be negative 2 negative 5 pi 6. Negative 5 pi 6 brings me over to quadrant 3. Negative 2 kicks me over to there. And then, of course, in both cases, we can just keep going around the circle. Everybody okay there? Now, this is nice because we can do a bunch of different representations. And our goal here is to kind of introduce the polar and things like that. You keep going to math, you end up in a course where that's all you work with. Some different pieces, and you start applying it a lot more. Because what happens is sometimes we need this guy because we want that negative. And sometimes we need this one. It just kind of rotates around. Okay? Which conceptually makes sense to us here in math, but sometimes it's kind of a pain because we're so used to there being an answer, not a representation. Okay? Something like that. So, I'm taking a test. I get this for my answer. And that's correct. And it's a short answer. Well, then that's fine. Well, what if it's a multiple guess question? And that's not one of the choices. One of these over here is one of the 4 choices. Well, first thing is just visualize where this is. And then when you're going through the choices, which one of those matches up to the same location? If you can just visualize where this guy is, you'd have it. Everybody okay there? There's that multiple representations. All right, so conversions. What we've got to be able to do is work back and forth between polar and rectangular. Sometimes we need polar, sometimes we need rectangular. The conversions, they're always these. We talked about earlier. Looks really familiar. Tangent one. This should look really familiar. It's just your Pythagorean theorem. Sometimes a little different form because of the R, but looks familiar. And we talked about these two. They just look like they're in a different form. But they're ones we know. So if I said convert, and let's go with root 2 pi fourths to rectangular. We're going to convert that to rectangular. So rectangular means I need an x and a y. I'm given an r and a theta, I need an x and a y. X equals root 2 cosine pi fourths. Y equals root 2 sine pi fourths. R cosine theta, R sine theta. Cosine of pi fourths is root 2 over 2. 2 sine of pi fourths, still root 2 over 2. So we're looking at 1 and 1. So this rectangular point is 1 comma 1. Now make sure, I mean, yeah, you can write that out and operate it, and you can come up with your x and y value, but make sure you understand the visualization that's going on here. What we're saying is, hey, if we go out 1, up 1, what do you know? That's root 2, that's pi fourths. That's what we're working with there. Right, so we have two representations, polar versus rectangular. Let's go convert negative 1 pi halves to rectangular. And if you get some non-standard ones, things like that, you got your calculator, but just kind of looking at some basic ones here, angles we should know. Negative 1 pi halves, x equals negative 1 cosine pi halves, y equals negative 1 sine pi halves. Well, cosine of pi halves is 0. Negative 1 times 0 is 0. Sine pi halves is 1. Negative 1, my point is 0, negative 1. And usually what I'll say, because a lot of times, if you're like me anyway, you mix up the positives and negatives sometimes. Especially when it comes to negatives, I'll drop negatives by mistake and things like that quite often. I always visualize where it's at. Quadrant 1, stay in quadrant 1. Yeah, I better have positive, positive. Y-axis, negative y-axis because it flipped down. Well, it makes sense, it's 0, negative 1. You can visualize where I'm at. So let's go the other way. Convert negative 1 root 3 to polar. So that same idea of kind of visualizing where you are, negative 1 root 3 would be quadrant 2. I'm going to go left 1, up root 3 units. I'm in quadrant 2. All right, so I'm expecting a quadrant 2 angle, right? Like that. All right. Well, I need an R value. All right, so for polar, remember we need R and theta. R squared, negative 1 squared, plus root 3 squared. All right, that's 4. So R is 2 or negative 2. Remember, R could be positive or negative. Okay. I always kind of look at the R as being positive And then if I need the negative one later, I can flip it to a different representation. Right? But I just want you to realize it could be either one, but it just affects what angle you're using. Then I go to my angles. Tangent theta, root 3 over negative 1. So I'm looking for tangent is negative root 3. If tangent's negative root 3, remember where that would be? Quadrant 2.
2 pi thirds.
Be 2 pi thirds. Tangents are a little tougher, right? Tangents are always tougher for me than sine and cosine. But I'm always going to think of the reference. So even though that's negative root 3, I'm just thinking of the root 3. Let me get my reference, and I'm going to stick it over in quadrant 2. And the reason I'm going to put it in quadrant 2, that's what I thought to begin with. So where's tangent root 3? You should be pretty clued in if it's root 3. You kind of know it's either pi 6 or pi thirds reference. It's one of the two. Okay? It's the taller ones, that's pi thirds, which translates to 2 pi thirds. So my point is 2 comma 2 pi thirds. Now, I always use tangents, personal preference. Okay? I'm not saying it's the best. I always use tangents. You could use sine or cosine here, because I do know r.
We're allowed to use our calculator on this, right?
Yeah, but these are still ones you're supposed to know.
Okay, but that means that if you can't remember, you can just do inverse tangent on negative
Yeah.
33.
And just remember, you have to place it in the right quadrant. So if I did sine, it would be y over r. Everybody agree with that?
Yeah.
All right, and so if I did sine y over r, it's going to tell me, even if I did it in my calculator, it'd tell me pi thirds, right? But I got to remember I'm in quadrant 2. So it's one of those two. It's that guy. Remember, your calculator is going to give you a reference. Keep focused on where you're supposed to be. Remember, we said initially, that guy's in 2. Okay? Look at that first. You know where you're supposed to be. If you're a cosine person, cosine theta would be negative 1 over 2. Negative 1/2. And if cosine is negative 1/2, we're looking at 2 pi thirds or 4 pi thirds, which I'm in quadrant 2. You got to be careful on those things. If you did this one on your calculator, tangent's negative root 3, it would actually tell you negative pi thirds. That's where I'm supposed to be. So remember, calculators are going to give you references that can help you. But make sure you place your reference in the right quadrant. So just always think ahead of time. Where am I supposed to be? That helps you with your positives and negatives. You can look at a rectangular coordinate and tell what quadrant you're supposed to be in. It's not hiding. All right, let's go with this. Let's see. Let's go equations. Let's convert r equals 2 to rectangular. So now we're not in a coordinate, we're actually on an equation. And we're going to convert r equals 2 to rectangular. So that means we just want x's and y's. Well, the only thing I have that represents with just an r with x's and y's is this guy. X squared plus y squared.
So that would be a circle one.
2 squared would be x squared plus y squared, and you're right, it's a circle. There's my rectangular equation. It would be a circle, centered at 0, 0, radius 2. Now let's just think visually what's going on here. This guy r equals 2. That means you're going out 2 units from the origin. And you weren't given an angle, so in every possible direction. That would create a circle. That make sense? Something like that. How about, let's go convert r equals sine theta to rectangular. Now this one's got a little bit of a problem here because I look over at my conversions and this is all there is. There's nothing else coming later. Those are the only 4 things back and forth between rectangular and polar. No tricks there. I wish I had an r sine theta instead of just a sine theta. Then I could put a y in there. Can I just stick an r over there by the sine of theta?
Multiply the other side by r as well.
Yes, I can. I can do anything I want as long as I do it to both sides. So if I wanted an r over here, yes, I can, as long as I multiply the left side by r also. So this would give me x squared plus y squared equals y. Now I'm in rectangular.
Wait.
Oh. R squared is x squared plus y squared. R sine theta is y. Now here's the nice thing about polar. Here's a circle. You should recognize a circle as being one very important thing. It's not a function. It doesn't pass the vertical line test, right? Right. Well, even if you were graphing, say, on your calculator, it would be y equals. Well, it's in function mode. You're graphing functions. Polar allows us to graph things that are not functions. This one's actually an ellipse. Or circle. No, this one's a circle shifted over. Sorry. Because I can bring the y over and then complete the square. I'm still seeing both squared, so still a circle, but the center's been moved. On something like that. Now those kind of things should sound familiar to you. I don't expect you to recognize every single one. But you should know immediately. You see a power on that y, that's not a function. Everybody agree with that? You know it's not a function. Okay, now let's look at your calculators for a few graphing things here. And first one we're going to graph r equals 2 sine theta. Actually, I just did let's do 2 cosine theta because we just did a sine one over here. All right, so on your calculators, remember where we went to the mode piece to change to parametric? You're going to go back to that mode and change it to polar. You'll see POL for polar. We are graphing angles, so make sure you're in radians. Did you figure yours out? Just follow along. It'd be the same idea. Okay? The same idea. All right. So we're in polar. We're in radians. Everybody agree?
Yes.
Okay. So go to your y equals, and all of a sudden it switches to r equals. Okay, and you can type in r equals 2 cosine, and then remember theta is that xt theta in button, your variable button. Unless you have an 85 or 86, then it has a theta on there on the screen. Some of it, you should see you have it. Yeah, so you remember where your theta is? Okay.
So like this little extra.
Okay. She'll get a circle. Now let's go back and remember how we talked about the window last time with parametric. Let's look at your window. Go to your window. And on parametric, you saw a T-min, T-max, T-step. Now you see a theta min, theta max, theta step at the top. Everybody agree?
Mm-hmm.
And the X and Y's are still how wide and tall your screen is. A big deal there. Okay. Theta min, theta max, typically 0 to 2 pi is good enough on the min and max. Typically. I mean, that's one time around the circle. Sometimes you only need 0 to pi. If you do 0 to 2 pi, it's going to graph it twice. If you really needed 0 to 4 pi, you're getting half the graph. But you can kind of tell that after you graph it once. Let's see what's going on. So usually 0 to 2 pi is a good place to start. And then there's that theta step, 0.1. If you've got something in there already, like 0.1, fine, leave it. But remember, 0.1, if I'm going from 0 to 2 pi, gives me about 63 points, which would give me a fairly smooth graph. Are you okay there? If you want to see the difference again, kind of like what we did before, change your theta step to 1 and regraph it, because now you're only plotting 7 points and connecting the dots. And you don't get as good a looking circle, right?
It just looks like it's third grader.
Yeah. So go with the 0.1. That gives you plenty of points to get a decent looking graph. Okay? Remember, if you want to lock your calculator up like Britain, take batteries out, reset it. Something like that.
I don't want to do that today, really.
All right, so you got a circle there. Let's look at this guy. So you should have your circle. How about this one? Let's go r equals 1 minus cosine theta. Okay. Let's go pull it. And now it's r.
Looks like has a little eye to it.
And then notice it's got another little go.
I was like, why does yours look different?
Everything else would be the same. We just had to figure out what are the changes.
Yeah.
All right. Everybody have the sketch?
It's like a whole whack.
Why is it like an egg?
Something to the lips. Should be looking at more of an elliptical shape. Everybody agree?
Yep, I'm agree.
Very strange.
We're just kind of getting some different shapes here. How about r equals 3 plus 2 sine theta? Let's go 3 plus 2 sine theta. And again, just practicing with some different looks. You're definitely seeing graphs that are not functions. They don't pass that vertical line test. So for those of you moving on into physics, engineering, things like that, you get a lot of particle motion. Particle motion revolves around. It's not a function movement. Okay? It's kind of like an orbit. And so you deal with a lot more polar in that respect because you're dealing with something that's moving in a pattern. Moving round and round. Everybody have that sketch? Looks like it gets a little flat on the bottom, something like that.
It's like it's got
Well, this one. Let's go r equals 3 sine 4 theta. Make sure you have the 4 theta in parentheses.
It's a flower.
This is what you call a rose. Looks like a flower. They just call them roses. How many petals are there? 8. There's 8 petals you see there, right? Okay. So it's called an 8-petal rose. No, you don't have to remember any of the names or anything like that. Okay. Where you're going to see roses, cardioids, which kind of looks like a heart. Limacons, which looks like a lima bean. You'll have ones with an inner circle, things like that. Again, the names aren't going to matter. Okay? But one of the things I do want you to realize, everybody has the 8 petals, and this is going to take us into the next class. Each one of those 8 petals has the same area. Sometimes it doesn't look like it on the calculator, the way the calculator gets stretched with the X direction of the Y, depending on just how you have your window. But each petal is the same size. Now, we have 8 petals. There was a 4 there. What if there was a 5 there? How many petals do you think you'd have? 10. So the sine's always going to double the petals. Let's look at a cosine one. Let's go r equals 2 cosine, and let's go 3 theta. Okay, the cosine's different. How many petals you have? 3. So the cosine produces the same number of petals as by the theta. The sine doubles it. Now again, and this one's a good one to look at because you see one of those petals going out along the x-axis. How far out does it go? 2. So on that previous graph, if you went back to it, each one of those petals, out to the point of the petal would be 3 units. The r would be 3. That distance out. And you see some different relationships there. You're not going to have to graph these by hand. Okay? You do need to understand what a polar coordinate means and how I can figure out where that point is for sure. Okay? But you won't have to graph these individual ones by hand, but we've got to be able to produce them and look at them and see some different things. Okay? So look at some of those different ones. All right, any question there?